Hello, this is Dr. Christy Patton-Lukes, and in this lesson we're going to talk about how we can calculate changes in state variables such as internal energy and enthalpy by using hypothetical process paths. So the idea here is going to be that we have a change in state from, well, we'll just say temperature 1, pressure 1 to temperature 2, pressure 2. We could calculate the change in any properties by actually following that process path, but that path may be very complex, or we might not even actually know what that path is. So we have an alternative, and that is to create a hypothetical process path. This hypothetical path could be as complex as I wish, but some simple paths might be to change temperatures, change pressures, and do this in some simple little steps. If I know how to do calculations based on changes in temperature or changes in pressure, then I'm going to have made my work a little bit easier. And I can choose any path. So I've shown one, which is going to be particularly useful when you take thermodynamics for chemical engineers. But we also could do something like just change the temperatures and then change the pressure. Any path could do, and I could even go through something where I went to higher temperatures and pressures before coming back down. So any path will do, just something that is going to be convenient for calculation purposes. So let's look at some of the different kinds of process path pieces that we might use. So the first one we're going to look at is holding the temperature constant and allowing the pressure to change. Now we're going to be trying to calculate state properties of fluids and how they change along these paths. So enthalpy and internal energy are going to be two of the most common that we're concerned about, and recall that they're related by H equals U plus PV. Now if you look at the change in H or the change in U, they are related by this expression. But delta H is delta U plus the delta PV. If one extends this using the product rule, remember from calculus, then this would be equivalent to also saying V delta P plus P delta V. And so that would be the relationship between the change in H and the change in U. Now let's look at this for various cases. So the first case we want to look at is for ideal gases. Ideal gases are a very useful special case. Sometimes I can use this as a way to validate more complex expressions for real gases. I can look at this as a limiting effect. But also I'm going to find that I can choose a hypothetical process path that says, let's take a magic step where we turn our substance into an ideal gas, do our calculations as if it were an ideal gas, and then magically turn it back into the real gas. These hypothetical paths do not need to ever physically happen or even be possible. So if we're going to consider ideal gases, one of the first things you need to know, and it's going to be proven to you in a thermodynamics course, but for our purposes, I'm going to tell you this is a fact. Internal energy for ideal gases is a function of temperature and only temperature. So at constant temperature, and I'm looking at constant temperature, change in pressure, delta U is going to be 0 if the temperature does not change. I also have PV equals RT for an ideal gas. Now that's the specific volume. And so if I want to know what the change in PV is, it's going to be the change in RT. R is the ideal gas constant. Word constant means I can bring that out of the derivative or the delta. And so delta PV is R delta T. That means that delta U plus delta PV is equal to delta U plus R delta T. And all of this is delta H. If I'm not letting that change in temperature occur, delta U goes to 0 delta T goes to 0, and so delta H is also 0 for an ideal gas at constant temperature. So this is to say that H for an ideal gas is a function of temperature and only temperature, and U for an ideal gas is a function of temperature and only temperature. Again, we will develop this more fully in a future course, but for now, that means that changes in pressure for ideal gases will be 0 for both enthalpy and internal energy. Okay, another special case, liquids and solids. Again, for solids and liquids, U is a function of temperature only. There's some minor changes that can happen with pressure, but they're really not going to be noticeable on the kinds of scales that we can measure. So at constant temperature, delta U is going to be 0 for solids and liquids. Now, unfortunately, the ideal gas law does not apply. So when I look at delta U plus delta PV, I need to still consider the delta PV piece of this. So delta H is delta U plus delta PV. Delta U for solids or liquids, we've said, is going to be 0. What about the delta PV? Well, delta PV, we've said, is going to be delta P times V plus delta V times P. Okay? I'm talking about solids and liquids, however. And one of the things that is most notable about solids and liquids is you can really squish them a lot, and they don't tend to change in volume very much. So no matter what happens, changes in volume tend to be very, very small. And so therefore I'm left with just the V delta P. So delta U for a solid or liquid is going to be approximately 0. Delta H for a solid or liquid will be V delta P. Now volumes are going to tend to be very small, but if you have a large change in pressure, then this is not going to be a trivial quantity. Our other case is going to be changes in temperature. So if I were to hold the pressure constant and change the temperature, how would I calculate changes in internal energy and enthalpy? To do this, we're going to have two terms we need to define, C sub V and C sub P. Now C sub P you have encountered, say, in a chemistry class. It's usually called the heat capacity in those courses. In thermodynamics and in chemical engineering, we call it the specific heat at constant pressure. And the specific heat at constant pressure is defined as the change in enthalpy with temperature while I hold the pressure constant. We have related to this C sub V. Now C sub V is how internal energy changes with temperature while holding the volume constant. So these are both specific heats. C sub P you've run into before. C sub V is probably new to you. Now, we can use these as a way of estimating changes in U or changes in H. So if I had a constant volume, so this little subscript here means constant volume. This little subscript here means constant pressure. It's a way of describing a path. So I can use these, and so I can use the C sub V definition to say that, if the derivative of U with respect to temperature on a constant volume path is C sub V, then delta U is going to be the integral from T1 to T2 of C sub V dt. So this is using the specific heat at constant volume. Now this will be exactly true for ideal gases. Okay, remember, U is a function of temperature only, meaning not volume, not pressure. This will be fairly close to true for solids and liquids. And it's going to be okay for real gases as long as the volume isn't changing too much. Okay, so we have this as an estimation tool. Delta U is CV dt. We similarly can use the definition of delta H. So we've said that C sub P is how enthalpy changes with temperature for a constant pressure path. And in this case, then if I take this and solve for H by integrating both sides, then delta H is the integral from T1 to T2 of C sub P dt. And if this is a constant pressure path, this is exactly correct. Okay? Now, this will be true for ideal gases, whether the pressure is constant or not, because enthalpy is going to be a function of temperature and temperature only. For real gases, if the pressure doesn't change too much, then this isn't going to be too bad, okay? But I am going to have to integrate C sub P. For solids and liquids, I'm going to need to use the definition for delta H is delta U plus delta PV. And so for solids and liquids, I find this. Now, recall if I let pressure be constant, so if delta P is 0 because pressure is constant, then delta H is going to be T1 to T2 C sub P dt. Okay? So let's look at an example. We want to find the change in enthalpy for a liquid that's undergoing a change in state from 1 atmosphere 25 degrees C to 5 atmospheres 100 degrees C. Now the properties of this liquid are given to us, and so we have the density, we have the molecular mass, and we have the specific heat as a function of temperature for this hypothetical substance. Now in this case, it specifies that temperature is going to be in degrees C, and so we want to find the change in enthalpy, so delta H, for this substance. So what we know is that delta H for this substance is going to be V delta P. This is a specific volume times change in pressure, plus the integral from T1 to T2 C sub P dt. Now we're going to need to know some information to relate the units properly. So as we do these calculations, I find that the gas constant is very helpful. Now, frequently people look at this with alarm because don't you realize this is a liquid? I'm going to use this simply as a conversion factor. And so we'll see where this is going to figure in just a moment. So again, we've got V delta P and Cp dt that needs to be integrated. So let's do these two steps separately. So first I'm going to look at the V delta P piece. Okay? Now V delta P, the volume, recall that density is 1 over the specific volume. And so specific volume, therefore, is going to be the reciprocal of the given density. So this means 1 cubic centimeter is 0.873 grams is my volume. Now my delta P, I'm going from 1 atmosphere to 5 atmospheres. So it's 5 atmospheres minus 1 atmosphere. So there's my delta P. But my units here are kind of nonsense, right? I have cubic centimeters, atmospheres, and grams. Okay, so although this is correct, it doesn't have meaningful units for energy. So what I do is I look at various values of R. And if you look at this piece right here has cubic centimeters, atmospheres, and gram moles. Well, I got grams. So 82.06 atmospheres, centimeters cubed, gram mole, Kelvin. Okay. Cubic centimeters, my atmospheres cancel. So now I have gram moles Kelvin per gram. You might look at that and say, I didn't improve the units at all. Normally we would want something like joules or something like that. So, not a problem. Where do I have one that has joules in gram moles and Kelvin? Well, how about let's use this one right here. That says that, I put that in the wrong spot. There we go, 8.314 joules per mole or gram mole Kelvin. Gram moles cancel, Kelvins cancel. I'm left with joules per gram. And so the change for the V delta P piece is 0.464 joules per gram. Okay? So you'll see that I just have a ratio of these two pieces. It gives me a conversion factor that gets me to energy units. If you try it a few times, you'll find that it's actually very convenient. Now, the other piece I needed to do was to integrate C sub P dt from T1 to T2. And the key to getting good answers is that you take the time and trouble to do the integration first and then evaluate at the endpoints. So 0.103 plus 1.39 times 10 to the negative fifth t dt. So I'm going to integrate this, so 0.103 t plus 1.39 times 10 to the minus fifth t squared over 2. And I'm going to evaluate this from 25 to 100. Now, since they specified temperatures in degrees C, I'm integrating with respect to DC, or temperature in degrees C. You want to always look at this. Sometimes the sources will have temperatures in kelvins. In that case, I must change the temperature units to Kelvin. In this particular case, then, I'm just going to take 0.103 times 100 plus 1.39 over 2 times 10 to the minus fifth times 100 squared minus 0.103 times 25 minus 1.39 times 10 to the minus fifth over 2 times 25 squared. And this answer is 162 joules per gram. Okay? Delta H is going to be the sum of these two. And if you had used the full number of sig figs here, you would find that this is approximately 163 joules per gram. This is 162.3 if one actually did full sig figs. So this concludes this little lesson. In the next lesson, we're going to talk about where on earth these values for C sub P and C sub V are going to come from.